Hello and welcome back to Introduction to General Relativity. In today's lecture, we will continue our discussion of solutions of Einstein's field equations for static and spherically symmetric spacetimes. In particular, we're going to continue our discussion of the Schwarzschild solution. And this time we're looking for a solution of Einstein's field equations that applies to the interiors of celestial bodies. So we're going to look for interior solutions of celestial bodies which are static, spherically symmetric. And what kind of material are these celestial bodies going to be seen to be made of? Well, we're going to be thinking about stars here, rather than, say, planets. And for a star, we're going to take as our model for a star not a solid but a liquid, right? You can imagine a star as a big, hot, boiling liquid. So we're going to look for spherically symmetric and static solutions of Einstein's field equations where the where the stress energy tensor takes the following form. It takes the perfect fluid form. Because we imagine that our star is just a liquid or gas, and can redistribute itself where the liquid comprising the celestial object can redistribute itself easily. And so we've got to start by making some assumptions in order to be able to compare the stress energy tensor with the metric solution that we have already derived on general grounds. And the observation we're going to use is that we should choose a direction for this u vector. Right? And since we're talking about a static solution here, we're going to choose that u is going to point in the t direction. And just for convenience sake, we put minus square root f. So as a vector, it's pointing directly in the t direction. And f here is exactly the f that appears in the vacuum metric. And yeah, as I emphasized earlier, the stress energy tensor star is meant to model stars. Hence, this time, for the first time ever, the abbreviation star is possibly the most appropriate one for that equation. Now, we've got the stress energy tensor. We have the Ricci tensor from the previous lecture. For general static spherically symmetric solutions of Einstein's field equations, so we just have to equate the two. Now, there's various incarnations of Einstein's field equations. We're going to use this trace reversed form. No, we are not. No, not today. No, we just apply Einstein's field equations in the usual form, or the originally, for this course, quoted form. GAB equals 8 pi TAB. We're going to apply them in this way. And we will obtain three independent equations, just as we did in the vacuum case. But to interpret these I'm going to be talking about a slightly different coordinate system. So this is an exercise to just do the substitutions of these equations. I'll just move this around so you can to make something explicit here. So you just take the Ricci tensor that we had before, the metric tensor that we had before, put it in the appropriate place of Einstein's field equations, and then work out the following components. Now I'll define what 0, 0, 1, 1, 2, 2 mean in a second, what particular components are being spoken of here. So we won't use exactly the same coordinates to evaluate these components as the vacuum coordinate system, but just a slightly rescaled version of it. And that makes for a slightly more compact solution. Okay, firstly I'll box up this equation here, these three equations. And so we've introduced a couple of basis covectors just to do the computation above. So we've introduced a basis of 4 covectors called E0 through 3. One of them you've more or less seen before. So these covectors make orthonormal with respect to the metric. And using these covectors, we introduce the following components. So this is slightly, it just rescales things and makes things slightly nicer when writing out the interior solution to use this particular basis. Of course, we didn't have to introduce this. We could have just done everything in the components given to us by the spherical symmetric coordinate system, but it slightly simplifies things to do it this way. There we go. So we've got 3 independent equations, just as before. And the first thing to note is look at equation 1 there, right? There's no f at all in there. So that can be pretty much just solved directly. And so rewriting equation 1 gives us the following equation, which relates h and the density, rho, and you can just straight away integrate that, right? And that's what you get. So I've introduced a constant here, mr, which takes the following form. It's really an integral of the density over the whole object with an additional constant which comes from the integration. But we want that this solution for GAB is smooth, as r goes to 0. So that implies that hr has to go to 1, and that means that a has to equal 0. It's the only way for that to work out. So we've already obtained a relationship between rho, the density, and h. Because the slices sigma that we used to derive our coordinate system 2 lectures ago, because they have to be space-like, then necessarily h, the coefficient of dr squared, well, that better be positive. Otherwise, you change something space-like to time-like, or at least not space-like. And so that implies actually a condition on R. And if rho is 0, then we can actually continue our interior solution for H onto the vacuum solution. And it is continued in that fashion if at the exterior radius of the celestial object, big M is precisely little m evaluated at R. So we found H, or we found the relationship between H and rho, to be more precise. Now all we need is F. And to make things slightly easier, we're going to write not f as f, but we're going to represent f as e to the 2 phi, where phi is some unknown function that we're solving for. And then we take a look at equation 2, and we substitute for our now known value of h and f, and we will obtain an equation for phi. And this equation phi relates r, p, rho, and m to phi. And we're not going to explicitly solve this equation here. You have to assume an equation of state on P and rho to get further. Now, we're not quite done yet. We haven't used all our equations, but before we do that, we'll just make a comment to interpret these quantities. So in the limit, the Newtonian limit, where like the pressure is much lower than the mass energy, and where mr is much less than r, so there isn't much mass energy around, this equation for phi reduces. I mean, the reason we introduce phi is that we want to identify it with the gravitational potential. So this equation for phi reduces to, well, one that should be familiar from Newtonian theory, namely, it's essentially just Poisson's equation for the gravitational potential. So we already knew that from our perturbation approach to linearized gravity, and now we've learnt it in the context of the Schwarzschild solution. Now we have one final equation. We haven't used up all our equations yet, but we have related these unknown functions f and h to rho and p. Now the thing about general relativity is you don't just specify rho and p and then you get f and h and then that's it. I mean, there's this complex interrelationship between the coordinate system, the distribution of stress energy, and the solution to Einstein's field equations, and these things influence each other in feedback loop, and we're going to see that when we substitute the two equations which we've derived into the third. We come up with a consistency, or an extra consistency condition. This third equation is a bright pain to derive. There's a lot of algebra going on here. And it relates the derivative of the pressure, of the density, and also the distribution of mass energy. And this is an equation that determines hydrostatic equilibrium for the object that we're under consideration, and it has a name. It's the Tolman-Oppenheimer-Volkoff equation. Of hydrostatic equilibrium. So this equation has to be satisfied in addition to the other two that determine, in a sense, f and h. Once you've gone ahead and substituted your pressure versus density relationship and you've satisfied all these equations, you'll have the metric. And the metric will take the following form. It is ds squared is minus e to the 2 phi dt squared plus 1 minus 2 little mr over r minus 1 dr squared plus r squared d big omega squared. And little m of r is as I defined it above. Oops. So this is the general form of a solution for a spherically symmetric static liquid body, celestial body. We could spend a considerable amount of time discussing the stability of various celestial bodies and getting into some very fascinating and beautiful topics, and eventually end up at the topics of neutron stars and black holes and so on. We won't pursue that in this course, although this is a wonderful advanced topic that you can follow up on. Instead, in the remaining part of the course, we're going to focus on some of the key predictions of general relativity and deriving the form of these predictions. And the most important predictions that we'll focus on in the next lecture is the motions of test bodies. In particular, we'll also focus on the motion of light in the presence of static spherically symmetric solutions. So that neatly brings us to the topic of geodesics of the Schwarzschild solution. And we're going to make our life simple. We're going to derive the motion of test bodies in the exterior region, right? It doesn't really make sense to follow the motion of a test body as it plunges into a star. Because you kind of know what's going to happen to the test body as it reaches the star. But it is kind of interesting to think about a test body dropping into a black hole. But we won't do that here. So we're going to derive the geodesics in the following lectures for test bodies and also for light rays in the exterior region. And that's where the radial coefficient is bigger than 2m. Now, our life is made a lot easier by the fact that the Schwarzschild solution is, in fact, rotationally invariant. So if you think about a celestial body and then a test body moving past a spherically symmetric test body, then you can already hope, I see, that no matter how the test body moves, you can exploit the symmetries of the solution to move the motion of the test body onto an equatorial plane. We'll get to that. But before that, there are in fact other symmetries that the Schwarzschild solution possesses, which greatly simplifies the derivation of geodesics. And in fact, there's another one not related to rotation invariance that I'd like to highlight now. And this is true actually for any killing vector field. So here's a little proposition, very, very easy to prove actually. So imagine we have a killing vector field, and we certainly have that in our case here. And suppose you have a geodesic and since it's a geodesic, it has a tangent UA. Then there is a constant of the motion you can derive, namely psi A contracted with UA is constant along the geodesic. And this is really simple and really easy to prove. We just apply the covariant derivative to this quantity. I'll write it the other way around. And apply the Leibniz rule, and then we'll almost be done. So note that the quantity in question is a scalar, right? That psi A contracted with UA is a scalar. Well, let's look at the two terms after applying the Leibniz rule. Well, the first one, this one's actually 0 because the tensor UAUB contracted against delta B psi B, delta A psi B must be, right? Delta B psi A, I apologize. That quantity there is going to be 0 because of Killing's equation. Because this is a Killing vector, it obeys this equation here, and the thing UA UB is symmetric, and therefore it's got to be 0. And the second thing is 0 because, well, that's a geodesic. Yeah? That's just the geodesic equation. So we've just learned that the derivative along the geodesic of psi a contracted with UA is constant, 0. So that symmetry will turn out to be quite handy when we are trying to derive the geodesics of test bodies and light rays for the Schwarzschild solution. Another symmetry, which I've already alluded to, is parity reflection, also rotation invariance, where if you can send theta to pi minus theta, and that'll be handy because it allows us to rotate a solution initially in some non-equatorial plane into the equatorial plane. So if the initial position and tangent vector lie in the equatorial plane, theta equals pi over 2, then so must the whole geodesic. And what that means is that you can just take one rotation and move the geodesic motion of any test body into the equatorial plane. Cool. All right. That's it in terms of general comment about the symmetries of the Schwarzschild solution and what it means for geodesics. In the coming lectures, we will derive the form of the geodesic and the motion of test bodies in the presence of the Schwarzschild solution. And then we will discuss and relate this to key predictions of general relativity that have been since confirmed. And then that really will draw us to the end and conclusion of this course. But that's it for now. Thank you very much, and I'll see you next time. Goodbye.